So greetings of the season. Today we are going to discuss introduction to organic chemistry. So in the higher secondary, actually the organic chemistry starts from hydrocarbon, alkyl halides, and then alcohols, and then carbonyl compounds, and then nitrogen compounds. Like this, the organic chemistry is taught. But before discussing all these chemical characteristics of important organic compounds and their synthesis and their importances and their reactions, the very idea on hybridization is very important, because whenever a reaction is taking place, how that particular compound is getting that particular shape, or how the attacking group is coming and how it is reacting with the active site, all these things you can very clearly understand only when you know the hybridization. See, the organic chemistry mainly deals with the compounds formed by carbon compounds. Carbon, its atomic number is 6. So its electronic configuration is 1s2, 2s2, 2p2. Suppose this electronic configuration is drawn, it is drawn like this: 1s2, 2s2 and 2p2. So when we draw the orbitals in this fashion, actually this is the increasing order of energy, but the p orbitals are degenerate and these 3 p orbitals are in equal energy. Suppose carbon in this electronic configuration, if it makes covalent bond with the hydrogen, there is only one possibility, that the hydrogen electron may come here and make a covalent bond. If such a chemical combination is possible, then methane will have the molecular formula CH2 with a structure C, one H and another H and the bond angle 90 degree. This is how it should be, because a covalent bond is formed when electrons are shared. Therefore, actually this is not taking place, because methane exists in CH4 and the structure is a tetrahedral. So we have to understand how the tetrahedral methane is formed. Actually carbon undergoes excitation, and during this excitation the one electron from 2s orbital is getting excited to one of the 2p orbitals which is vacant. This is how the excitation is taking place. The hybridization you can clearly understand if the energy diagram is drawn from down to up. Suppose, let me explain like this. So here is the 1s orbital, and here is the 2s orbital, and here the 2p orbital, where the 3 orbitals are degenerate. So for carbon excited state, the 1s orbital has 2 electrons and the 2s has 1 electron, and the 1 electron from the 2s orbital is now excited to the 2p orbital. Now this is like this. Suppose if a carbon makes a covalent bond in this stage, that is carbon with the excitation only, then methane will not be of a tetrahedral shape, because all the 3 electrons in the 2p orbitals are perpendicular, mutually perpendicular. One is in the x-axis, one is in the y-axis, and the other one is in the z-axis. Whereas the 2s, one electron, is non-directional. Therefore, it will not be of that shape. So something has undergone. What has happened is, the 1,2s orbital and the 3p orbital, they get mixed up. They are getting hybridized. See, hybridization, orbital mixing, and orbital overlap, these are all 3 different things. They are not the same. This hybridization, So when they are hybridized, they are forming four equally energized orbital, and whose energy will be higher than the 2s orbital and lower than the 2p orbital, depending upon the combination, how many p orbitals are combined and how many s orbitals are combined. So this combination of 3 p orbitals and 1 s orbital, it is called sp3 hybridization, and the hybridized orbitals will be 4 in number, and their energy will be lesser than that of p orbital and greater than that of s orbital. It is somewhere here, with all having 1 electron each. So these hybridized orbitals, they will try to be as far apart from each other. Therefore, the maximum separation is attained only when the bond angle is 109 degree 30 minutes. 109 degree. So each hybridized orbital is having 1 electron each. Therefore, the hydrogen s orbital can make covalent bond like this, and this is how the methane is formed with a bond angle of 109 degree 30 minutes. Now, if you take nitrogen, nitrogen electronic configuration is 1s2, 2s2 and 2p3. So the atomic number of nitrogen is 7. If nitrogen undergoes sp3 hybridization, the nitrogen excited, the 1 electron from the 2s orbital will get paired with one of the electrons of 2p orbital. Now nitrogen undergoes sp3 hybridization. So ammonia, nitrogen, again the tetrahedral structure is formed, but in one of the vertices of the tetrahedron, the lone pair is occupied, and the remaining form covalent bond with hydrogen. Now the bond angle is 107 degree 28 minutes because of the lone pair bond pair interaction. It is pushed down. Originally the tetrahedral bond angle is 109 degree 30 minutes, but now because of the lone pair bond pair interaction, the ammonia is in a pyramidal shape. The bond angle becomes 107 degree 28 minutes. But if you take oxygen, the next element, which has the atomic number 8, the electronic configuration is 1s2, 2s2, 2p4. See, it is already having a paired electron in the 2p orbital, 1s2, 2s2, 2p4. Now, oxygen on excitation, the one of the 2s orbitals, 2s electrons, is getting excited to 2p orbital, and thus the oxygen is getting 2 paired electrons. So even then it is sp3 hybridized. See, the hybridization of the carbon in methane is sp3. The hybridization of nitrogen in ammonia is also sp3. The hybridization of oxygen in water molecule is also sp3. Now oxygen is at the center. Again 4 vertices for the tetrahedron, but here the 2 places are occupied by the 2 lone pair of electrons, the electrons which are not involved in the bond formation, and the other 2, they form the covalent bond with hydrogen. That is why in water molecule the bond angle is 104 degree 30 minutes. So it is going down because now the repulsion is by 2 lone pairs of electrons, and again bond pair lone pair interaction, and the bond angle is going down. So this is how the hybridization is understood. So our main idea is to understand the hybridization involved in carbon atom in methane molecule. Now let me explain the sp2 hybridization.
Okay.
sp2 hybridization, again you can clearly understand this if you draw the orbital diagrams like this. Carbon with the 6 atomic number. So this is 1s, 1s with 2 electrons, and 2s with 2 electrons, and 2p with 2 electrons. So you have to understand like this, because this is the increasing order of energy. So when the carbon is excited, one of the electrons from 2s orbital is getting promoted to the 2p orbital. Now the hybridization, only 3 orbitals are involved. One s orbital and 2 p orbitals. Now the resulting 3 orbitals are called the sp2 hybridized orbitals, which are finding their energy between 2p and 2s, somewhere here. But this time the p orbital contribution is less, because in the case of sp3 hybridized orbital, there are 3 orbitals from p and 1 orbital from s. Therefore s character is only 25%. Remaining 75% is of the character of p orbitals. But this time only 3 orbitals are hybridized, among which 2 are from p and 1 is from s. Therefore only 33.3% of s orbital contribution and 66.6% the p orbital contribution. So now the energy, the resultant energy of the 3 sp2 hybridized orbitals will be somewhere here in between s and p. But one unhybridized p orbital will remain in its own energy level here. So these 3 sp2 hybridized orbitals are having 1 electron each, and the one unhybridized orbital is having 1 electron. With this structure, with this distribution, it is going to combine with the hydrogen, and you can understand this combination like this. See, carbon, the 3 hybridized orbitals are trying to be as far as they can be separated from each other due to minimize the repulsion. So they are taking 120-degree angle among them. So it is a triangular planar. The angle is 120-degree. So the unhybridized orbital is perpendicular to this. You can assume this. If the hybridized orbitals are in the plane of the blackboard, then the unhybridized p orbital is perpendicular to the plane of the blackboard. So this is how sp2 hybridized carbon is. Now, if this combines with another sp2 hybridized carbon, the sp2 hybridized orbital and hybridized orbital will form the overlap, direct overlap. And there are two more sp2 hybridized orbitals. Then this will combine with s orbital of hydrogen with 1 electron, and a covalent bond is formed. And this will combine with another hydrogen with 1 electron, and a covalent bond is formed. And this carbon also combines with 2 more hydrogen atoms and forming covalent bond. And this carbon is also having a perpendicular unhybridized p orbital. And both the perpendicular unhybridized p orbitals of these 2 carbons, they form a lateral conjugation, a lateral combination. So this forms side to side overlap. Whereas this is direct overlap, this is side to side overlap. Therefore, between carbon and carbon, one sigma bond which is formed by the combination of 2 sp2 hybridized orbitals, direct overlap, and one pi orbital which is due to the lateral overlap of the perpendicular unhybridized p orbitals. You should never mistake that this lobe forms one pi bond and this lobe forms another pi bond. Both the lobes, they form one pi bond. So because this is one full orbital, this is not 2 separate things, it's one full orbital. So this is how the ethylene structure is there. So ethylene CH2 double bond CH2, the structure is C, H, H, double bond C, H, H, the double bond, one is sigma bond and the other one is the pi bond. So this hybridization idea and how this bond is formed between 2 carbon atoms, these are all very important when you come to reaction mechanisms. See, pi electron and the electrophile coming and attacking, and then the electron jumping, and one carbon becoming positively charged and the other carbon becoming negatively charged. How these charge separations, how these combinations are taking place, what happens, why an unsaturated hydrocarbon is undergoing addition reaction, why a saturated hydrocarbon is undergoing substitution reaction. All these things you can understand only when you clearly understand the hybridization patterns. Now, the other hybridization is sp hybridization. See, in this case, I directly write the carbon excited electronic configuration. In 1s orbital, 2 electrons. In 2s orbital, 1 electron. And in 2p orbital, all the 3 orbitals have 1 electron each. This is after excitation. Originally, here was 2 and here was 2. But now, one of the electrons of 2s orbital is excited to 2p orbital. So now, it is having 3 electrons in the p orbital and 1 electron in the s orbital. Now, the hybridization is between 1 p orbital and 1 s orbital. So what happens now? 50% contribution is by s orbital and 50% contribution is by p orbital. Therefore, the hybridized orbital's energy will be nearly close to s, here, somewhere here, unlike the sp3 and sp2. See, sp3 hybridized orbital may be here, the energy. When it becomes sp2, it is less than that. When it becomes sp, it is much less than that. But always, all these hybridized orbitals are having energies in between p and s because it is a combination of p and s. Now, the hybridized, sp hybridized orbitals have 2 electrons and the unhybridized p orbital is remaining in its own energy with 2 electrons. So, this is how the distribution of electrons. Now what happens? So the carbon is now having sp hybridized orbitals too. As the 2 orbitals, they try to be as far apart as separated, the angle between these 2 orbitals will be 180. So similarly, another carbon with another 2 orbitals, sp hybridized orbitals. But in this case, what happens? The unhybridized p orbital, they are perpendicular. See, the one which is in the plane of the blackboard is also perpendicular. The one which is perpendicular to the plane of the blackboard is also perpendicular. So these 2 perpendicular orbitals are unhybridized p orbitals. Now what happens? This orbital can combine with the hydrogen with 1 electron in 1s orbital, and this can combine with another hydrogen with 1 electron in the 1s orbital. But these 2 unhybridized p orbitals can have the lateral overlap and they can form pi bond, and these 2 lobes, they can form another pi bond. So this is the structure of acetylene. So the acetylene, carbon and carbon, there are 3 bonds, 2 pi and 1 sigma, and on the other side sigma bond with the 2 hydrogen atoms. This is how acetylene structure is. So acetylene is linear in structure. It is in linear in structure with the triple bond between carbon and carbon, and the triple bond, 1 is sigma and 2 pi bonds are there. So only when you understand this hybridization and how these bonds are formed between carbon and other elements, you can understand the carbon chemistry well. And let us continue in the next video. Thank you.